Long before people walked the Earth, even before the dinosaurs, before the first signs of life appeared on this planet, before anything existed at all. The Big Bang, the birth of our universe. From this new matter, the first galaxies took shape. Nebulae formed inside the galaxies, and inside the nebulae, the first stars were born. The Sun was about to make its appearance in the same way, surrounded by a rotating disk of dust and gas. Gravity pulled the dust particles together, and they turned into huge masses that grew and attracted other masses, future planets. The gases gathered in the Sun, which finally lit up. The planets grew thanks to large and small meteorites that rained down from the sky. The energy of each new impact was transformed into heat that gradually warmed up the young planets. Eventually, these became the worlds we know today: Jupiter, Saturn, Mars, and of course, Earth. But what happened to the heat that was accumulated while our planet was being formed? It's still there, hidden in the innermost layers of the Earth's core, and it's constantly reinforced by natural radioactivity. The heat is continually transmitted to other layers before being freed into space. During its journey toward the surface, the heat moves semi-fluid rocks it meets along the way. Like water boiling in a pot, the rocks in each layer rise upward and shed their heat. Then they fall and get heated again.
Earth has begun to take on its final form. A crust, a skin so thin it would be less than a sheet of paper, were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. Here's how it might have happened. At first, Cretans and one continent called had the planet all to themselves. Then, around 500 million years later, Antarctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Antarctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? So what does this mean at the surface? Two things. First, magma being burped up along the ridges. Those places like Iceland where the Earth is tearing itself asunder is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know, or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know.
When plates move apart, You have a divergent boundary. Magma from the mantle wells up, creating new oceanic crust. As those plates pull apart, on the opposite sides of them, they crash into continental crust, which is less dense and thus more buoyant, causing the oceanic crust to dive under. This is known as a convergent boundary or a subduction zone. Oceanic crust dives back into the mantle where the rock eventually melts. Some of this will rise through the crust and form volcanoes. When continental crust crashes into continental crust, the similar density prevents one from diving under the other. This is called a collision boundary. The plates push up against each other, creating mountain ridges. There is one more type of boundary, where plates slide against one another. As they slide against each other, energy is stored, and when the plates ultimately slip, all that energy is released in the form of an earthquake.
Hundreds of little earthquakes shake the planet every day, but most pass unnoticed. They usually occur along the boundaries of the thin plates that cover the Earth like an eggshell. Driven by the heat deep within the Earth's core, the plates grind against each other along lines called faults. When the plate's motion is blocked, stress builds up. Finally, the fault gives way. The released energy races through the Earth in the form of seismic waves. For a quake to measure one number higher on the Richter scale, it must release about 30 times as much energy as the number below it. Every year, about 100,000 earthquakes rumble through the ground hard enough for people to feel them. Of these, only about 1,000 are strong enough to damage property. The greatest recorded earthquake ever to hit North America measured a massive 9.2. The tremor struck Alaska on March 28, 1964. A camera on board a ship docked in Valdez recorded the draining of the entire harbor as a chasm opened up on the sea floor. There's no stopping the surface of the Earth from changing and moving, so engineers are focusing on ways to create better buildings, highways, and bridges, structures that will remain safe and stay in one piece the next time the Earth begins to shake.
Hidden deep beneath the waves of the Western Pacific lies the Marianas Trench, the deepest point of all the oceans.
To get a sense of just how deep trenches are, if we take the height of Mount Everest, we would still have about a mile of water above us before we get to the ocean's surface.
But what created this mysterious scar in the Earth's crust? Their maps revealed that the Marianas Trench is just a tiny fraction of a network of enormous underwater canyons stretching right around the planet. But that wasn't all. Running parallel to the trench, on the other side of the Pacific, the map showed a giant underwater mountain range, the East Pacific Ridge. The underwater ridges and trenches sit on the boundaries between tectonic plates. The East Pacific Ridge and the Marianas Trench lie on opposite edges of the Pacific Plate. 50 million years ago, the Pacific Plate slipped under the edge of the Philippine Plate. As it bent and dived into the Earth's mantle, it formed the colossal Marianas Trench. Crust bubbled up at the ridge 170 million years ago. It was light and buoyant. But as it traveled 10,000 miles across the plate, it cooled and became compact and dense. Over millions of years, the dense crust got heavier and began to sink into the mantle below.
Volcanoes mostly occur along destructive and constructive plate boundaries, where plates are pushed together or dragged apart. Cracks or weaknesses allow magma to rise up from below the Earth's crust. Pressure builds up, which then releases suddenly, causing the magma to explode. A volcanic eruption. Magma that reaches the Earth's surface is called lava. This molten lava eventually cools to form new rock. After more eruptions over time, a mound of rock builds up, forming a cone-shaped volcano. Volcanoes all have the same key structure. A collection of magma underneath the volcano forms a hot, bubbling furnace called the magma chamber. The main vent allows this magma to escape. And secondary vents are smaller outlets the magma can travel through. The caved-in surface is called the crater. It's created after an eruption blows the top off the volcano. Eruptions occur when pressure forces magma from the chamber up the main vent towards the crater. If the ash and mud from a volcanic eruption mix with rainwater or snow, it creates fast-moving mud flows. The hot lava and overwhelming mud flows can destroy huge areas. Scientists believe that volcanoes formed Earth's first atmosphere by spewing water vapor, sulfur dioxide, nitrogen and carbon dioxide into the air. And volcanic eruptions continue to contribute to the carbon cycle, crucial to life, by releasing carbon dioxide. They can go through long periods of being very active. But they may also become dormant, not erupting for hundreds or thousands of years. And eventually, they can become extinct, just leaving a cone-shaped hill that never erupts again.
White Island, as with all of New Zealand, sits right on the rim at the junction of the Pacific and Australian plates. It's a collision area where the floor of the Pacific Ocean dives deep below the Australian plate in what is called a subduction zone. The seafloor is buckled and pulled down into deep trenches, and the friction triggers powerful earthquakes as the Pacific plate is slowly consumed. Even here, magma flows from underwater volcanoes as rocks are melted and recycled.
Volcanoes usually occur at plate boundaries, where the continents collide. When they hit, they release unimaginable energy, punching up molten rock from deep inside the Earth. The Pacific Ring of Fire marks a whole series of these plate edges. It's got half the world's active volcanoes. Hawaii is more than 2,000 miles from the nearest collision zone. Beneath the ocean floor is a mysterious area of super hot liquid rock. Hot enough to melt a hole through the Pacific plate, punching up fresh lava. It's called a hot spot. The ocean floor is creeping gradually northwest at 3 inches a year, but the hot spot under it doesn't move. A volcanic island builds up, but as it moves away from the hot spot, it is cut off from the source of lava and dies. Over the hot spot, a new volcano forms.
All this used to be solid rock. And all that rock disappeared to the ocean below.
"2 million years ago, the island fell apart. 300 square miles, 20 trillion tons of rock dumped in the Pacific Ocean. shape. The rock slide really has taken a bite out of the island.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
After 200 million years, this is the result. But the plates are interlocked. That's why, when they shift, the jerky movement along the edges that separate them causes what we call earthquakes. Most of the earthquakes recorded in the world aren't very strong, but sometimes a particularly great one causes destruction and death. Earthquakes also occur at the sea bottom. When that happens, they can sometimes displace the water column and originate waves. These waves are best known by their Japanese name, tsunami, which simply means harbor wave. Regular sea waves caused by the wind are very different from tsunami waves. Let's find out why. Wind blowing over the sea can only move the upper layer of water, forming waves but not affecting movements deeper down. The water particles near the surface move with a circular motion, which helps to propagate the wave along. Deep down, the water particles don't move. The strength with which these waves reach the coastline depends exclusively on the movement in the first few meters of water. A tsunami, on the other hand, can be generated at the bottom of the sea. In case of a strong earthquake, the sea floor abruptly deforms and vertically displaces the overlying water. The entire water column is disturbed by the uplift or subsidence of the sea floor. This sudden movement releases a great impulse of energy, which is transferred to the whole column of water between the surface and the sea floor. In this case, the water deep down moves as well, as deep as 1,000, 2,000, 3,000 meters. Currently in use in the Pacific and Indian Oceans give advance warning when a tsunami is generated. These systems rely on sensors placed at the sea bottom, which measure variations in the water above and transmit an alarm via floating buoys and satellite link-ups with observation stations on the coast. Once generated, tsunami waves in the open sea travel very, very fast, up to 800 kilometers per hour. They can cover thousands of kilometers and approach coast far from their point of origin with great energy. In the open sea, the waves are rarely over a meter high and are very long, so they're imperceptible. A ship in open sea, for instance, wouldn't notice anything out of the ordinary. The speed of a tsunami wave depends on the depth of the water the wave is traveling through. Approaching the shore, the tsunami's speed diminishes, although it's still much, much faster than an ordinary wave. Also, wave amplitudes will increase dramatically. This is due to the fact that the tsunami's energy flux, which is dependent on both its wave speed and wave height, remains nearly constant. Consequently, as the tsunami's speed diminishes as it travels into shallower water, its height grows. This huge and fast-moving mass of water shifts an entire column of water from the sea floor to the surface. Approaching the coast with a destructive force far superior to any wind-generated wave, it can advance hundreds of meters inland. That's why, even if it isn't very high, a tsunami wave can still cause serious damage along a coastline. When the trough of the wave first reaches the coast, the tsunami appears to make the sea withdraw, often quite consistently, leaving harbors and beaches dry. This is exactly what happened along the coast of Thailand on the morning of December 26, 2004. A tsunami generated by the strongest earthquake of the past 40 years off the island of Sumatra spread death and destruction along the coasts of the Indian Ocean. The project is another important contribution towards research aimed at studying and better understanding the Earth, the only planet that's home to life. We need to protect ourselves and to protect the Earth.